Okay, we considered the theorem 2.13 the other day, and uh, okay, so before we go to the next slide, okay, so we defined the multiplication of two matrices, okay, and so that when each matrix represents a linear transformation from one space to another, right? Which maps certain vector to the given matrix times a vector when you consider that transformation. And then this product will represent the composite of those of two matrices. And we have a little bit more than that. Actually, this matrix multiplication between of certain vector that can be represented, that can be understood representing certain linear transformation from one vector space to another, where A is representing certain matrix when some bases are given. So matrix multiplication may be understood as a simple matrix multiplication from from Fn to Fm space, but that can be regarded as a mapping, as a linear mapping from one n-dimensional vector space to another n-dimensional vector space. And this matrix multiplication can be understood to represent the composite of two matrices, two linear mappings. So what I mean is, so here from V to say W, then so we have this mapping T, and then if I have another mapping, say S to Z, then X vector will be mapped to T of S, T of X, then S of T of X will be the final destination, right? And everything here, these mappings can be understood by certain V vector in Fn space that is mapped to some vector in Fm space, and the emissive vector is just A times the V. And then we have another mapping from Fm to say say Fl, and that is this S mapping may be represented by B, and we get this. So B of A, so B times A times X, that is representing this composite operation. We want to define a product, meaning we want to define a single one matrix which maps this X to this final result. Okay, so how do we define this? Given A and B, if I have such here, if A represents the mapping, okay, let me change the text as in the textbook. If this is the case, so here mapping B, and if this guy is represented by A, then we get A times B times X. So A times B times X, that's what we want to represent. And we want to represent this as a single matrix, single C. We want to define a single matrix C representing this. And the ith row, jth column entry of C is obtained by multiplying the ith row of A times the jth column of a B matrix. So A ith row first column, ith row kth column times kth column, kth row, jth column entry of B, and then you change this, you let 1, 2, A is M by L matrix. So, yeah. So this is the definition of this product we considered, we introduced. So that was the definition. And then the theorem I just explained is this. So, okay, so we can find this a single matrix C whose ith row, jth column entry can be computed by this expression. But if C, if C is obtained by multiplying A and B, what you can do is you can multiply A to the first column of B to obtain the first column of C matrix. And A times the B2 up to A times Bn. So if B has n columns, then this product obtained by this definition can be obtained column-wise, column by column. So the definition estimates each entry in certain row and column. Okay. Now the theorem or the note at the bottom says each column of the matrix can be computed column by column. Right? How you need to multiply the matrix on the left to each column of the matrix on the right. So there are two ways to visualize this, to derive this product. And the meaning was this. We want to find a single matrix representing this composite of two linear operations. So, as I said, column J of A times B is a linear. Okay, yeah. So this is what I already mentioned. Now, theorem 2.14 says, suppose that V and W are finite dimensional vector spaces having some basis beta and gamma, and T is a linear mapping from V to W. Then for each vector U, okay, what is this? This is the coordinate. This is the coefficients of the image T of U when the basis gamma is used. Please note that I have V space and W space. I have U in the domain, and that is mapped to T of U in W space. And beta is a basis for the domain, and gamma is a basis for the codomain. So the T of U with bracket of gamma, this one, that is representing the coefficients of the linear combination when T of U is expressed in terms of the basis gamma in the codomain. What is this? This is a matrix representing this linear transformation. How do we obtain this? You map each basis vector in basis vector in the domain, which is beta, right? And then you represent each vector in the range with respect to gamma. Then the coefficients, okay, used in this linear combination, in this expression, linear combination, those will be defining this matrix. So for example, if beta consists of, say, V1 up to Vn, then T with this bracket is a matrix. The first column considers the coefficients which are required to express T of V1, where V1 is the first vector in beta. When you represent this T of V1, since T of V1 is a vector in W space, definitely gamma will be used to represent this vector in W. Okay, so that will be the first column of this matrix. Then you map the next vector in beta and represent it with respect to the basis gamma. You do this up to Vn. You identify these column vectors and construct this matrix. Then that will be this matrix. So this matrix is not related with you. This matrix, okay, this matrix is that matrix is defined once two bases, one basis for the domain and the other basis for the codomain are given. Theorem 2.14 says, given this matrix, if I want to find the coordinate of T of u for some u vector, for some u, what you need to do is you can directly compute the left hand side, or you identify this matrix above here, and then you identify the coefficients which are used to represent u vector in the domain. Okay, and then you can multiply these two. Okay, then you will get this result on the left. So that is the claim of 2.14. Okay, so 2.14 says we have this claim in the red box. So two vectors will be the same. That is the claim. Okay, so on the left we have the what is this? That is the coefficients of the linear combination when the image, okay, so when the image T of u is expressed in terms of gamma, and that happens in the codomain. Okay, And what is this? That is the coefficients of the linear combination when u vector is expressed in terms of beta in the domain. Okay. And once you get this vector, if you multiply the vector with the matrix representing the linear transformation, you can identify these coefficients of the image vector. Okay. So the vector on the left represents the coefficients when the image T of U is expressed in terms of the basis gamma. And the vector U with respect to beta, that is the coefficients, okay, of U vector in the domain when beta is used as a basis. And this theorem says in either way you will get the same vector. Before I express some meaning, let me consider the proof. So let me fix this U vector and let me define the linear transformation F, which is a mapping from the scalar field to V. Okay, F is the set of numbers and V is the domain, and F is a mapping which maps any real number, any scalar A to the scalar multiple A times U. And I want to define G, that is a linear mapping. That is a mapping from the same scalar field F to W by which maps A to A times T of U. Okay? Then F and G are well defined. For any number A, we can find the image, right? And you can easily show that the mapping is a linear map. They are linear mappings. Now, for the F space, we can use this number 1 as the basis, right? Basis. Then, and we know that this mapping G will be the composite of T and F. And identify the column vectors as matrices, and we have the following. So the image, this vector, these coefficients of the image is T of U is the image of 1 under G mapping, right? When 1 is mapped under G, G maps any number A to that number multiple of T of U. So T of U is 1 times the T of U. So T of U is number 1 times T of U. So that is the image of 1 under mapping G. So we have this. Okay. And what does that mean? G of 1. And that means, what is this? If you remember this definition, Given this G mapping, G is a mapping from F to W. G is a mapping from F to W. And in the domain F, I'm using this standard basis of 1 for F. So G of 1 represents, okay, this one, what does that mean? I'm just considering the coefficients when G of 1, and 1 is the basis vector of F space, right? So this matrix will be just representing the linear transformation G when this number 1 is the standard basis of the domain and gamma is the basis of the codomain. Do you understand what I'm saying? Please note that G is a mapping from F to W, and in the domain F, we are using alpha, which is just a set of 1 as a basis, and W is a vector space with gamma. So to find the matrix representing this G, what do I need to do? You need to map each vector in the basis of the domain and then represent it with respect to the basis of the codomain, which is the gamma. So that is what I am doing here in the second term. So the coordinate of G of 1 with respect to gamma just identifies the matrix representing this G when alpha is used as a basis and gamma is used as the basis of the codomain. Now, since G is the composite of T and F, we have this. And previously, when you have this composite, mapping with these bases, that could be split like this, right? And I want to apply a similar trick here. G is a mapping from F to W, and F is a mapping from F to W with alpha, the set of 1, as the standard basis. And, oops, not W, but V. And in case of F, the beta is a basis for the codomain. So when you look at this term, that will be the same as this. That's the trick I considered here. In this inequality, I considered that trick, right? I considered this idea, right? So I want to apply a similar trick here. So this matrix will be just the coordinate of F1. But what is F1? F1 is just a U vector. So we get this. So what is the meaning of this? Uh, so what is the meaning of this? So we have a linear mapping from V to W. And in V, we have a basis beta. That is a basis. And gamma is the basis for W space. And this within this V and W, okay, given this beta and gamma, I can find this matrix. Okay, so let me call this guy as A for simplicity. Then, for any U vector, you can find T of U, right? So in order to find the T of U, there are two ways. That's what the theorem says. Okay, please, you need to understand the meaning of the theorem. So, okay, we can find T of U directly by applying this T mapping. So to find this T of U, okay, you can apply this mapping directly. Or given this U and beta, you can find this vector. Where is it? In Fn space. And then I can multiply this A matrix. Then you get some vector in Fm space. So A times this vector can be estimated. Let me, okay. That will be what does the theorem say? That is, this guy is the coordinate of the image with respect to gamma. Then how can I reconstruct this T of U from here to this? You can consider a linear combination, a linear, sorry, a linear combination of the vectors in gamma using as coefficients. So this is second way to get the image. You first identify this vector. Of course, you need to calculate the matrix A. So let me write down this A matrix here. So A is the matrix representing this linear transformation when beta and gamma are used as basis. You can find this. So given U vector, you identify the vector in Fn space, you estimate A, and then you multiply A with this vector, then you get this one. So you consider a linear combination of the vectors in gamma with these numbers as the coefficients. So it seems that the approach 2 is a detour, right? It takes several calculations. So you want to apply the first, the number one approach, okay? But it seems that depending on the situation, sometimes instead of applying the first approach, this alternative, this detour, may be more efficient in some situation. We will see some examples. So the theorem says in order to get this T of U, you have two ways. Number one, you can apply this mapping T directly. Number two, you calculate these coefficients of U when as in terms of beta, you identify this matrix A, and then you multiply those two to get this vector, and then you consider the linear combination. One thing you need to notice is that in this upper part, everything is related with general vector spaces. So those operations from U to T of U happens within general vector spaces. On the other hand, at the bottom here, you are considering the calculations. The calculations happen in in Fn or Fm spaces. They are numbers. Okay. When I say general vector spaces, the vector spaces may consist of matrices, functions, polynomials, and so on, right? But here at the bottom, we play with just numbers. A is a matrix with numbers, and these vectors are also some vectors with some numeric values. So that's why we sometimes consider this a detour, the second approach, instead of the first one. So let us consider some example. Suppose that we have a mapping T from P3 to P2 space, and that is a linear mapping defined by which maps any cubic polynomial to its derivative. And we want to use the standard ordered basis for the domain and codomain, which means beta consists of 1, x, x squared, and x cubed. And gamma consists of 1, x, and x squared. And we already considered how to find this A matrix. Please remember that the first column represents the coefficients when T of 1 is used as a linear combination of the vectors in gamma, right? This is T of 1. What is this? The derivative of the constant function 1 is 0. And when I use gamma as a basis, then this 0 vector can be written as 0 times 1 plus 0 times x plus 0 times x squared. So these three zeros go to the first column. In a similar way, we can consider the derivatives of x, x squared, and x cubed, and so on. So if we do that, since we considered this, so let me skip the other parts. Then A will be this 3 by 4 matrix. Okay? Now, if I consider any polynomial in the domain, say P, with this, okay, then what is the derivative of this? Derivative will be this. This is the derivative of this. So the approach 1, which directly considers this operation, that is the first approach. Okay. The second approach is the following. Given this vector P in the domain, okay, that is a vector in P3 space in the domain. We want to describe that vector in terms of the beta, the basis of the domain. So this is the domain. So for our vector in the domain, we use the basis for the domain. And the coordinate, I mean, when you represent this in terms of standard basis, then these numbers, 2, -4, 1, and 3, will be the coefficients of the vector P when beta is used as a basis. So this is the this one. Now, if I multiply A matrix with this vector, and then if you do the calculation as we did, you get this. Then what does this three numbers imply? That will be the image of this T of P using gamma as a basis. So in order to construct the T of P, so that means T of P can be obtained as a linear combination of the basis gamma, which is 1x x squared. And then if you multiply -4 to the first vector and 2 to the second vector and 9 to the third vector, and if you add them, you get this image of P vector. And that is the same as this. So this approach to get this image is the second approach. Okay. So as I said, it's you may think that the first approach may be more direct and intuitive, but we will see some more examples later why this second approach may be more efficient in some situations. But anyway, the point of the theorem 2.14 is that the image T of P can be obtained in two ways. Please remember this. So let A be an m by m matrix with some numbers chosen from a field F. Then, given this A matrix, from now on, we define a mapping L sub A to represent a mapping from Fn to Fm, which maps any vector in Fn to A times x. So any vector in Fn will be mapped to A times x in Fm space. Okay, so and this mapping will be called left multiplication transformation, and symbolically we will use this L sub A to denote this left multiplication operation. So given this A matrix, if x consists of this 1, 3, -1, L sub A maps this x vector to A times x. Then when A is an m by n matrix and L sub A is the corresponding left multiplication, then you can easily show that this L sub A is a linear mapping. That is trivial. And when beta and gamma are standard ordered basis for Fn and Fm, then the matrix representing this L sub A transformation with respect to beta and gamma will be A matrix. And this is trivial, I guess. You can easily prove that. And if L sub A equals L sub B as a mapping, then A and B must be identical. Also, this mapping corresponding to A plus B will be the sum of these two linear transformations. And when you multiply any number A to A matrix, then you get this. You may have a linear transformation corresponding to A times A, and that will be the same as A times L sub A. And if T is linear mapping, then there will be there will be for any t from Fn to Fm is a linear, then there will be some C matrix representing, and this T is left multiplication by C, and this C will be unique. And if E is on n by P, this will be the same as this. Okay, and these are quite straightforward. I mean, when you look at just the symbols, you may doubt, but the proof is quite trivial. If you just think about the meaning of each notation, it is truly simple. So you can read it. You can read it yourself. Let me skip the proof. And matrix multiplication we defined is associative, meaning given three matrices and their sizes allow allow them allow this multiplication in this order, meaning the number of columns in A matrix matches the number of rows in B matrix, and the number of columns in B matrix matches the number of rows in C matrix, so that I can multiply A times B and then multiply C matrix later. Okay, and that will be the same as this one, meaning given these three matrices, you can multiply any two first, B and C first, or A and B first, and then you can multiply the remaining one later, as long as you keep this order. Please note that matrix multiplication is not commutative, right? Due to this, you cannot switch the order of the matrix multiplication, but since we have this, I mean, by the definition of the matrix multiplication, we can easily show that it satisfies the associative rule. So far we considered matrix representation of the linear transformation, and then we interpreted matrix multiplication, okay, to represent a linear transformation from one vector space to another, right? So mapping T from V to W, that is the same, that can be understood by a mapping from Fn to Fm represented by some matrix A, and if you consider L sub A operation from Fn to Fm, the operation at the bottom exactly copies the mapping above here. Only difference is that in the above, you play with actual vectors. I mean, the vectors, the general vectors in general vector spaces. But at the bottom, you consider special types of vectors in Fn or Fm spaces. And instead of considering the operation of T, you need to consider matrix and vector multiplication. So that's what we considered so far, and then we extended this matrix multiplication to mimic the composite of two functions. So we considered matrix multiplication to mimic the composite of two linear transformations. Suppose that V and W are vector spaces and T is a linear mapping. We say, we say some function u from W to V. Please note that T is a mapping from V to W and U is a mapping from W to V that is said to be an inverse of T if this composite mapping. So T of U is a mapping from W to W, right? So T of TU is a mapping from W to W. And if that mapping is the identity mapping, and UT, the composite function from V to V, is also identity in V space, then we say U is an inverse of T. And if T has an inverse, then we say T is invertible. Even though I said U is on inverse, we can show that if T is invertible, the inverse will be unique. So people usually call D inverse because it is unique. And that inverse matrix is denoted by this. So we have this following. This is simple, right? Why is it so? Because you can multiply TU with U inverse T inverse. Then they are all functions. So I can they are all composite functions. So T U U inverse T inverse, and these two operations between T and T inverse will be the identity mapping. So we get T identity T inverse, and identity can be neglected. That is the identity again. So that means the inverse of the composite of T and U will be the U inverse times T inverse in the opposite order, in the reverse order. Okay. And so if this T to the negative 1 represents the inverse of T, then T inverse will generate the identity mapping by definition. Then, so if I interpret this left hand side in terms of T mapping, this guy on the right is the inverse of T, right? But if I interpret the left hand side in terms of T inverse, then the guy on the left will be the inverse of T inverse, right? Do you understand what I'm saying? So if I look at this expression, T composite of T and T inverse will generate the identity mapping. So if I interpret the left hand side with respect to T, then the guy on the right is the inverse of the one on the left. But if I interpret in terms with respect to the T inverse on the right, then T on the left will be its inverse. So T will be the inverse of, right? T inverse of T inverse. And that also means T inverse is also invertible, if T is invertible. And and in theorem 2.5 says if V and W are finite dimensional vector spaces and if T is a linear mapping, then so in theorem 2.5 we consider the following. So if T is 1 to 1, then T is onto, then the rank of T will be the same as the dimension of the domain, right? These are equivalent, right? Because T is 1 to 1. That means T is 1 to 1. That means the the kernel or the null space of T consists of only the 0 vector, right? So that the nullity, the dimension of the null space will be 0. T is onto, mean that means the column space, so the range of T range of the mapping equals the codomain W. If that's the case, then the rank of this mapping will be the same as the dimension of the whole space, W space. If that's the case, then the rank nullity theorem implies that the nullity plus rank will be always the dimension of the domain V. That is the fact in any circumstance. Okay? So in statement A, if T is 1 to 1, then that means the nullity is 0. Then rank and dimension of V will be the same. If B is onto, then rank of T and the dimension of W are the same. Then since the dimension yeah, yes, then just a second, rank T is onto, yes, dimension of W, if the, yes, right, yes, if T is onto, range is W, so the rank, since the rank is the same as, okay, then, oh, sorry, we have one assumption here. The V and W have the same equal dimensions. So In that case, the dimension, so that equals the dimension of V. So in that case, the from this rank nullity theorem, the nullity will be zero as well. And in both represents that the rank and the dimension of the domain are the same. So that's what we considered previously. And and we know that a function will be invertible if the mapping is one-to-one and onto. Okay? Then by theorem 2.5, we have the following fact. So given this linear transformation from V to W, and if V and W have equal dimensions, then T is invertible if and only if T is one-to-one and onto. Then by the rank nullity theorem, the rank must be the dimension of V space. Okay? Then your mapping will be invertible. So in example 1, so we have a mapping T from P1 to R2 space. P1 is a space of a polynomial of degree 1 or less. So any general vector in that space will be of A plus Bx form. And let me map this A plus Bx vector to a pair of A and A plus B in R2 space. Then you can show that if you consider the composite of T and this mapping, you get the identity mapping, right? I mean, once A plus Bx is given, and once this vector is mapped to A and A plus B vector, and then if I apply this mapping, then given two vectors, given two numbers, given a pair of C and D, you get C, which is A. So this is C and this is D. A plus D minus C will be A plus B minus A times X will be A plus BX. So this mapping is actual inverse. And you can show that this is a linear mapping, and right? So in example 1, this inverse mapping is given, right? And we just confirmed that this is actually the inverse of this T mapping. The question will be then, if I do not give you this second mapping, and if I give you only T, how can I find the inverse mapping? That's what many people are interested in, right? So please think about it. Okay. So if I do not give you this one, how can I find this? How can I derive this from this one? Well, you may consider the definition, and that is one way to get this, the inverse of T, but there may be some alternative way to get this T inverse, and we will think about it later. And in the previous example, I mentioned that T inverse will be a linear mapping, but is it some special case? No. Theorem 2.17 says if T is a linear and invertible mapping, then T inverse will be also linear and of course invertible. Linear and of course invertible. And if I assume that this T is a linear mapping, then this T is one-to-one and onto, one-to-one onto, and dimension of V and dimension of W are equal and so on. Okay? So in order to prove that T inverse is a linear mapping, let me choose any two arbitrary vectors from the domain W. Okay. Now, since my T is one-to-one and onto, when I choose y1, y1 will be an image of some vector, and that vector will be unique. And y2 is also an image of some vector, some unique vector. So there will be two vectors x1 and x2 in the domain in V space, okay, x1 and x2 in V, such that T of x1 equals y1 and T of x2 equals y2, and x1 and x2 will be unique and they always exist because the mapping is invertible, meaning the mapping is one-to-one and onto, right? Then since the T of x1 is y1, T inverse will map y1 back to x1 and x2 will be mapped to x1, y2 will be mapped to x2. Now, if I consider cy1 plus y2 under T inverse, then since y1 is T of x1 and y2 is a T of x2, we have this. And now T is linear. I'm just using the fact that T is a linear mapping. So this expression will be the same as this. Now at this step, I want to use the fact that T inverse is the image of T. Then whatever you have here, the composite of T inverse and T will send this vector to itself. And as I said, x1 is the image of y1 under T inverse, and x2 is also the image of y2 under T inverse. So if I replace x1 and x2 by those, we get T inverse of cy1 plus y2 equals c times T inverse of y1 plus T inverse of y2. That conforms the linearity of T inverse mapping. And as I said, if T is an invertible linear transformation, and then as I said, dimension of V and dimension of W must be the same because the mapping is one-to-one and onto. Okay, so you can easily check this fact. If the dimensions are different, at least one of them being one-to-one or being onto, they cannot be satisfied. You can easily derive the contradiction, right? So those were the invertibility of a linear transformation. And in this slide, I want to consider the case with a matrix. We say, given some matrix A, some n by m matrix, we say it is invertible if there is another matrix B such that A times B and B times of A are both the identity matrix. Then we say A is invertible and B will be called an inverse of A matrix. Okay. And in case similarly to the linear operation, the linear mapping, if a matrix is invertible, then the matrix will be unique. Because if there is another invertible matrix, then that means B is an inverse. So A times of B and B times of A will be the identity. And if I assume that C is another inverse, then A times C and C times of A will be also the identity mapping matrix. So C will be the same as C times identity, and identity is the same as A times B, and matrix multiplication is associative. So instead of multiplying A and B first, you may multiply C and A first, and then you can multiply B later. But once you multiply C and A, you get the identity matrix. And identity times the B will be just the B matrix. So if I assume that there is another inverse matrix, then that matrix will be the same as the original inverse matrix. So the inverse will be unique, and that inverse matrix is denoted by this, a to the negative inverse. And and you can verify that one matrix is the inverse of the other. Oh, similarly to the previous case, if A and B are both invertible, and if they are both n by m matrix, then A times B times B inverse A inverse will be A times B inverse times A inverse, which is A times identity times A inverse, which is A times A inverse, which is the identity matrix. So this B inverse A inverse is the inverse of A times B, right? And so given this, if you multiply 5, 7 to 3 with 3, negative 7, negative 2, 5, you can check when they are multiplied, you get the identity matrix. Before we consider this, let me just uh, compare the inverse with the transpose. So if A given A, the transpose of A, and then if you take the transpose again, you get A matrix. Okay? But at this point, this A can be any m by n matrix. The inverse of A, and if you take one more time, inverse one more time, you get this A. But here, this A must be on n by n matrix only. Okay? And this matrix must be invertible. Not all n by m matrix is invertible. Okay? So for example, the zero matrix is not invertible. But in case of the transpose, I can take the transpose of the zero matrix. And when A and B allow their multiplication, the transpose of the product will be B transpose A transpose. The inverse of A times B will be B inverse times A inverse. Some number multiple of A, if we take the transpose, that will be C times A transpose. Even when A is invertible, the inverse of this will be, is not C times A inverse, but 1 over C times A inverse. So in order for 1 over C to have a meaning, this C cannot be 0. In case of the sum of two matrices of the same size, its transpose will be A transpose plus B transpose. Even when A and B are both invertible, even when A and B are invertible. Okay? So sometimes people make a mistake, right? And yeah, sometimes you may make a mistake. So please be careful. And some properties are shared between this transpose and the inverse, but some are not shared. So please be careful. Now, suppose that V and W are finite dimensional vector spaces with some basis, beta and gamma, and T is a linear mapping. Okay? If T is invertible as a mapping from V to W, then the claim here is that the matrix derived from this beta and gamma basis will be also invertible in the sense of matrix invertibility. Okay? And furthermore, the matrix representing the inverse of T will be the inverse of this matrix. Okay? And actually this comes from simple fact, but since I don't have enough time to read or check this proof, let me continue from this slide next time to let me prove this theorem, because this theorem is simple, but that is important. Okay, so you need to consider two things. First, if T is invertible, then this matrix will be invertible regardless of this beta and gamma for any basis. For any basis, this matrix will be invertible. The invertibility of T is not related with beta or gamma, right? So if T is invertible, then the matrix with respect to beta and gamma will be invertible. And additionally, the matrix representing this inverse of T can be easily obtained from the matrix representing this T. You can just simply take the inverse. We didn't study how to get this inverse matrix yet, but okay, so this matrix comes from the matrix of T. So let me continue next time. Okay, thank you for listening and see you next time.